Hello everybody and welcome back to Environmental Science 101. I am your host, Professor Cedor. Today we do air. You might notice that the space around it is left blank, and that is intentional. The other thing that is not intentional, there is a storm going on right now where I am, so you might hear some noises in the background. I apologize, but I cannot control it. Okay, so what are our objectives? First is to go through the biography of Earth. Now this includes connecting our concept of evolution to the history of Earth and to this concept of deep time. We are going to talk about the Holocene, which is the very, very last little sliver of time on Earth on the big timeline, and talk about the changes in terms of biodiversity and human impacts through the Holocene. We will talk about the Earth's atmosphere, its motions at the planetary scale, its chemistry, and we can connect some elements of Earth's creation and its biography to the motions and chemistry of the atmosphere. And then we'll take it one step further and talk about how atmospheric circulation and patterns influence temperature and precipitation, and therefore climate, and therefore ecology, and everything else that we've talked about so far. After this, we will look in a different direction. We will go to the Yale EPI framework for environmental policymaking. Now, what is this? We're going to be looking at the environmental scores of different countries, essentially, and the components that make up those scores, and we might see how this is connected to the other things when we do it. Okay. Finally, we will try to put these things into context. So biodiversity, ecosystem services, air pollution, policymaking, and then we will look specifically at the Clean Air Act and some of its components. Okay. There's going to be 4 sections for this. So the first 2 are going to be the biography of the Earth, right? So part of it is its birth all the way up to replicators, DNA, coming online, which is quite early in Earth's history. Then the rest of it is going to be from life emerging, coming online, all the way to the present day. We'll have a section on the atmosphere. We'll have a section on air pollution, and that is it for this one. Awesome. So to start with, we have our biography of the Earth. So this is our beautiful planet. Mostly water. This is a nice photo of it. If you go and Google search blue marble, it will pull this up. This one is my favorite photo of the Earth. And if you didn't have a personal favorite photo of the Earth, then now you do. It's this one. Until you send me one better. So do it. Okay. So there is this question of how old the Earth is and how it got started. Now, these days, it's easy to almost take for granted that we have answers to this question. Actually, we have a billion answers, depending on how much you want to look into it. But this was not always the case, right? Really, we can imagine the standpoint of somebody a long, long time ago, one of our ancestor humans, sitting outside and looking up at the night sky and trying to figure out the order behind things and how the Earth got here. And what sort of conclusions they would be able to draw from that, right? So from the problem-solving perspective as scientists, right, we want to figure out an upper bound on how old the Earth is, and then slowly kind of work from that, right? If we can establish one date in time for sure, and say that the Earth happened, or after that, right, that helps narrow down things a lot, right? On the other hand, the process from the human side does not work that way. The process from the human side is you go around finding things, and your idea for how old the Earth is kind of gets bigger and bigger and bigger over time, or you could get around that entirely and just call the Earth infinitely old, which, again, to go back to our original question of being outside, looking up at the stars and asking how old is the Earth, if you drew the conclusion that the Earth was infinitely old, you are actually probably smarter than trying to guess. And our clear night sky, right, inspiring wonder and leading to sciences as well as technology and others, actually does come up in our story of evolution at the very end. Clear night sky might be a requirement to have technology and talk to other things. Enough on that for now. Okay, so this question of the age of the Earth and how old it is has been asked by many people since time eternal, as much as I don't like that phrase, right? We'll go back to Aristotle first, 400 BC. We will skip a long way ahead to Calvin, modern or even slightly pre-modern, depending on how you want to draw the line. And then we will go to the modern day estimation for the age of the Earth, which comes in the 1950s. Okay, so we will start with Aristotle, famous philosopher, had this idea that you could estimate the age of the Earth by looking at how salty the oceans are and looking at how much salt comes off of rivers into the ocean. And that if you knew those two things, and you could kind of calculate how the ocean has been filling up with more and more salt over time, you could work backwards to get the age of the Earth. Much later, something in like the 19th century, somebody actually tried this method and got an age that was laughably low, like impossibly low. Stupid, young Earth ideas, not good. But this idea runs into problems, right? First and foremost, salt gets removed from circulation in the oceans and laid down as these rocks called evaporates. In other words, the amount of salt in the ocean is not something that just started at zero and kept going up, but this was the idea. If we jump ahead a little bit to more modern day, right, we have Lord Baron Kelvin here, who the temperature is named after, was a physicist and argumentative person. He had this idea that you could estimate the age of the Earth based on what I call the loaf of bread idea, right? So here's the metaphor. If you know how hot the oven is, and you know how hot the loaf of bread is, then you can figure out how long it has been since the loaf of bread was inside of the oven. That's it. That's the whole idea that he had. The loaf of bread being Earth, and the oven being the sun. And that's what he tried to calculate it off of, using cooling rates. Once again, got an age that was far too low, almost laughably so. Would have been better off just saying that the Earth were infinitely old and avoided some problems in scientific development along the way. But that's not how they saw it. Finally, right, we have our modern day age, right, which comes from the dating of space rocks. These are meteorites, are the same age as the entire solar system, formed when the entire solar system formed, and Earth formed at the same time as the rest of the solar system. So if you can establish a date for the meteorite, then you have a date for the Earth, and this is exactly what happened, right? So we are in a still post-war era, a lot of military technology that is no longer being used for war, and so a lot of folks just go out with that technology and test different things and investigate, right? There is this huge explosion in Earth science knowledge using war technology in the post-war period, and this follows in that trend. They did uranium lead isotope dating. It's the same concept as carbon dating, but with stuff that is way older on the scale of billions of years old. And in fact, this is a really good estimate considering how long ago it was. In fact, this is kind of the baseline starting point estimate for the age of the Earth today. It's actually kind of amazing that this has not really changed at all since this happened in the 50s. And like any good science, right, we have our error bars, plus or minus resolution. As a fun fact, where did this meteorite hit the Earth? Maybe we heard it, right? Is our meteor crater. This is the Cañón Diablo meteorite. This hole is quite a bit bigger than it looks. These are people and these are vehicles and structures down in here. Might even be able to notice, right, we have some rock layers being exposed. This thing is big, and it's located in Arizona. Maybe check it out if you've never been, right? So we got Phoenix here. We can go all the way up to Meteor Crater. Okay, this makes it look like it's kind of close, maybe 2.5 hours from Phoenix, but totally worth it. Okay, so this, if we go back, right, 4.55 billion years, plus or minus 70, is going to establish our starting point on this timeline, right, where our Earth timeline begins, and that is this thing. Now, do you need to remember all the terms on this thing? Do we need to really dig in? No, absolutely not. We just need to remember that we start out here on the timeline, and the way that you work through it is like this. So we're going from right to left, from bottom to top. This makes sense in the sense that, right, older rocks are deeper down, and this is constructed by and for geologists. But we need to remember, we're here on the timeline to start, right, beginning of our Earth. Okay, now, we have our beginning of the Earth. There's like one thing that we need to talk about that happens before the Earth forms that is important. Okay, this is our periodic table. Matter is made up of particles. We know this. Those particles come in different personalities, essentially. Number of protons determines the personality of the atom, and these are arranged here in an orderly way. Right. So basic stuff, right? Hydrogen, helium, has the smallest number of protons and other things in the nucleus of the atom. In other words, it's the simplest stuff that forms. And so we should not be surprised that the universe is primarily hydrogen and helium. In fact, this would have been the first stuff to form. The question arises of where these heavier elements come from. And the answer is going to be through stars going through the supernova process. So as they go through the process of supernova, hydrogen starts to fuse together to form helium, which starts to fuse together to form other stuff. And if you notice, we kind of glossed over the step. We'll talk about what happens with helium in a moment. So just to recap, right? This is our universe today. 90+% hydrogen, some helium, mainly created by fusion in stars, and then everything else is a tiny fraction of it. And yet, is this what Earth looks like, at least at the crustal scale? No, right? We are super duper concentrated in all of these heavier elements, right? Oxygen, silicon, aluminum, right? Heavier stuff that has to be made, not like hydrogen or helium. And the question is, where does this come from? And this part, do we need to worry about the mechanisms? No, but we can see helium particles, right, in some sort of collapsing star going supernova. They fuse together under the immense pressure and weight of it. And while two of them could come together to form beryllium, what actually happens is that three of them come together. And we put three heliums together, right? 3 4s together is going to make our carbon-12, which is essential for life because it forms things like rings and chains, which are needed if you want to build stuff. Okay. This is where we really need to start paying attention. So all that stuff, the supernova, the creation of the heavier elements, is before our solar system starts to form, just as a baseline. Now, we have got our interstellar cloud of gas and dust. Interstellar as in far from any other star. And over a long period of time, all this different gas and dust, right? Dust being made up of these heavier elements, is going to come together under the force of gravity. And it's going to compress over time. The rotational elements are going to be the only thing that doesn't cancel out, is one way to think of it. You can also imagine spinning pizza dough, right? And it is going to begin rotating as it collapses in on itself. The stuff in the center becomes the sun. There's a big popping sound as the sun starts to ignite and fusion starts to happen, right? And that rotation is conserved in the planets, right? So we have these planetary bodies slowly growing larger through our process of accretion as they rotate around the sun until we get our modern day planets. What's important to remember, right, is that these things are rotating around and that rotation never stopped. This is going to come back. Yes. And as far as how we know this, you can look at other solar systems forming today with telescopes and see the resemblance. Right. So the Earth begins to differentiate after it has formed. So we are one step after this, right? Our Earth has formed, condensed out of the solar nebula, begins to differentiate into layers. We don't have to learn these. We could maybe remember that the Earth formed similar to a glass jar full of dirt and sticks and bugs, right? And you imagine shaking that jar up, and then you set it down and just let it settle. The dense stuff settles to the bottom, and the lighter stuff floats up to the top. It's the same process. We have a collision as our next event, where it officially becomes Earth. Collision that causes a lot of material to spin off and begin rotating and form the moon. We have water, which comes to Earth. This is a complicated problem, all right, multiple solutions, and has changed over even the past few years. There's this idea that it's most likely two different sources. So some is hydrogen that was already on the Earth, and some of it comes from comets and asteroids, bringing the water with it. Okay, so we've got water on Earth, we've got an Earth formed, we've got our moon. Now we are ready for life. Now, I'm going to skim over the mechanisms in between, or else we'll be here all day, right? So we have an Earth with water that has been formed. It's got a moon. We have inorganic compounds that start to form amino acids, right? Nucleotides. They come together, and we don't need to worry about exactly why or how, but they form some sort of system which can replicate itself and which can sustain itself. Now, about right here, we can also imagine the formation of these things, which are replicators, right? So some sort of replicator molecule interacting with the other stuff in the molecular soup, and it binds in such a way, right, that the replicator can split and make more of itself. And this is going to be the starting point of another concept that we have talking about. So these replicator molecules that come online here at this stage, they are still around. In fact, there are many of them inside of all of this. So these are the genes, right? These are the things that actually reproduce. We don't need to worry about the mechanisms exactly of how it comes about. We do need to understand that these are replicators. Replicators come online, and then, as we'll see, evolution can take it from here and do all the rest of the history of life on Earth, with a couple exceptions, which is what we are going to check into next. See you then.